It gives me immense pleasure to invite our third speaker for today. He is the CEO and Managing Director of Ossicle Private Limited, a passionate student of science with 13 plus years of qualitative experience in business management, commercial operations, leading and establishing a company in a large geography. He is an effective communicator and public speaker who has given numerous breakthrough presentations and has worked extensively in Singapore, Middle East, and Indian subcontinent markets. Please put your hands together, ladies and gentlemen, for Mr. Ravi Mohan DABRAL. With an huge round of applause, ladies and gentlemen. He's going to deliver the talk on the potential of single-walled nanotubes in the rubber industry. So please welcome him with a huge round of applause, ladies and gentlemen. Welcome, sir.
Thank you so much. Okay, this one up. Good afternoon, ladies and gentlemen. First of all, thank you for having me here. And to start this presentation, let me, by all my gratitude, thank IRMRA for this wonderful, all-benefiting journey of 60 years. I believe it is because of the institutions like you, the whole technological aspirational level and the quality of overall industry, not only one company, is increasing. So please accept my thanks for that. Oxygen, carbon, silicon, aluminum, that is Oxial. These are four most used elements by mankind in that particular order. And our vision and our aim is to improve the daily used material by mankind. We are a global company and one of the biggest in nanotechnology, not only in terms of the size or our global network, but also in sheer terms of the material and applications that we work with. We specialize in single-wall carbon nanotube, which can improve 70% of the material known to man. 70%. So what is single-wall carbon nanotube? It is one atom of carbon bonded with three other atoms in a shape of graphene-like platelet structure. You roll it into a tube, it will be called a single-wall carbon nanotube. You can also call it as graphene tubes. And because of its unique structure, they have some exceptional properties. They are excellent conductor. They are 5 times lighter than copper and about more conductive than copper. They are stronger than steel in tensile direction, about 100 times. Their thermal stability is extremely high, 1000 degrees Celsius, and they have got extremely high aspect ratio, up to 1 million times. If you compare it with other additives, and my ambit is not only with rubber, I'm talking about all the polymer additives. If you compare it with all other polymer additives, you would find that single-wall carbon nanotubes are used in very, very low concentrations. The reason is very high aspect ratio, length to diameter ratio, and its hollow structure. Because single-wall carbon nanotube do not have anything inside them, they are hollow. That is the reason why they can be used to bring about a significant change in the properties of the material at very, very low concentration. This is just an illustration where you can see if we put similar weight of microparticle, nanofiber, and single-wall carbon nanotube into a similar kind of a volume, single-wall carbon nanotube would give much larger coverage of the area, hence their properties. So how do they look when they are dispersed properly? You see, this is a SEM slide under various magnification. As I go deeper and deeper, you'd be able to see these fluorescent lines, which is a percolating network of single-wall carbon nanotube. So what essentially is done, single-wall carbon nanotube form their own 3D conductive network throughout the matrix of the polymer. And this single point provides you all the properties of single-wall carbon nanotube exhibited in your end polymer. This also becomes a key factor or a key quality sweet point for the polymer chemist who is trying to mix these few ppms of single-wall carbon nanotube into his compound. For example, the task of a polymer chemist or a compounder would be to use 1 gram of single-wall carbon nanotube into 1 ton of material, and the challenge clearly becomes how to disperse them effectively, right? Oxiel is world's biggest manufacturer of single-wall carbon nanotube. In 2014, we had a capacity of producing about 10 tons. In 2018, we can produce 50 tons of single-wall carbon nanotubes per year. We are also a very responsible company. That means we look at where we sell our product and how it is being used. We are first and only REACH compliant company for single-wall carbon nanotube in the world. Now, coming on to the topic of immediate relevance, if you see or if you research single-wall carbon nanotube usage in rubber polymers or in elastomers, through last 15 years, there has been tremendous work. Let me add a little bit about when and how single-wall carbon nanotubes were discovered. There are references of single-wall carbon nanotube in literature which are almost about 40-year-old, but in 1991, a Japanese scientist had a patent for them. The patent belonged to IBM and has recently expired. Since 1991 till today, 2017, there have been very, very few usages, sorry, 2018, I stand corrected. There have been a very, very few instances of commercial usage of single-wall carbon nanotube, despite all the properties that I mentioned and explained with you. That brings about a very important question. Why is that? Why is this wonderful material, which can bring about so much of a change, which can improve properties of your polymer, was not used in this big length of time? The primary reason was the commercial availability. If there is no commercial availability, how would you be able to use it? And then there was a secondary reason. The primary reason was taken care of when Oxiel was formed. In 2009, we started producing single-wall carbon nanotube at a commercial pace and a commercial rate, and also at a commercial price, which made it easier for even the most commoditized application to use single-wall carbon nanotube. I'm talking commercials here in terms of the price. But at the same time, there is a secondary challenge associated, which I just explained a few minutes back, which is dispersing these single-wall carbon nanotube in a huge matrix, a compounding challenge. Now, the end of any technology is to make life easier. And as my colleague and friend here was talking about disruptive technologies, which should change the way we live, which should change the way we use material, but for easier, for better. So Oxiel did not restrict itself to only producing single-wall carbon nanotube. We also put in a lot of effort into making its end use easier. Traditional approach of using carbon nanotubes in elastomers or any polymer, when I say elastomer, it goes for any polymer. So the traditional use was using raw single-wall carbon nanotube, but we have changed it, and we have tried to bring in the concentrates of single-wall carbon nanotube in the carrier media, which is known to compounders, particularly in rubber case, which is known to rubber compounders, the carrier media which you can use very easily. This particular presentation from now on, I would like to restrict to EPDM. So I would talk about the tests and the results we got in EPDM when we use single-wall carbon nanotube in it. We analyzed two properties primarily. One, mechanical, second, electrical conductivity. And then we try to use the industry standard procedure. There is a lab procedure. Most of us here have been through research background and understand what a lab procedure is for an academic paper and how alienated that can be to an actual industry procedure. We try to bring it. If you see all the tests here, if you see all the processes here, if you read the equipment names, internal mixtures, Banbury's and all those, we tried to keep the whole approach as near as possible to actual industry applications. In compound A, where we were testing mechanical properties, to take out all the biases which were possible, we used two kinds of matrices. When I say matrix, it is a 10% compound of single-walled carbon nanotube in a carrier. We use DOA and DOS. And these were the recipes which were there, which were used for single-walled carbon nanotube. What we did was, we took a reference compound and we kept on increasing the dosage of single-walled carbon nanotube through this matrix, through this carrier at 0.1, 0.15, and 0.2%, as you can see. And the results were very nice. As you can see, there was a marked increase in tear strength with rapid increase in single-walled carbon nanotube concentration. Now let me get into depth of it. We saw that there was no significant impact on hardness of single-walled of the whole material, of the whole compound after addition of single-walled carbon nanotube, which is very important in case of extremely hard, high hardness compounds. This particularly is a pain point when you compare it with other fillers like carbon black and other fillers who have high aspect ratio, because addition of them increases the hardness a lot. You would also find it very interesting to note here that between DOA and DOS, there are different results. Now, this is to be kept in mind that single-walled carbon nanotube alone would not result in end product. It has to be combined with a compounding technique and carrier. Everything is relevant in that case. Hence, you can see two different kind of results with two different kind of carriers. There was a significant improvement in tensile strength of DOS-based concentrate, as you can see. And surprisingly, there was no adverse effect on elongation at break. The maximum effect we observed was in the range of 0 to 5%. Again, you have to compare this with other traditional material, like carbon black. When you add it, what it does to your compound. There was a very good improvement in tear strength, as you can see. This is attributed to the structure, the three-dimensional percolating structure I just showed and talked about. There was a minor impact of DOA-based compound on moduli, as you can see. But again, comparing it with other traditional fillers, it was much, much less than that. Same with DOS-based. Again, there is a difference between DOA and DOS-based master batch. Now, testing the conductivity. Conductivity is another part of rubber which we require not always, but at some times it is very essential to bring in conductivity to the whole part, especially in dynamic applications. And I'm pretty sure you would know that even the tires which touch the road have to have some conductivity in them. So this was the recipe used, and we used 0.26% of single-walled carbon nanotube in it. There was one more objective of using carbon nanotube in these compounds, that was to bring about color. We wanted to explore the possibility of bringing in conductivity with color by using single-walled carbon nanotube. Why that? Because right now, there is no such combination possible. If you want a conductive compound, you would have to put in carbon black, which would essentially make the whole compound black. Colored rubber compounds are very, very interesting for some applications like solid tires. And then there are other possibilities also. So this is the kind of color we could get by adding 0.26% of single-walled carbon nanotube. As you can see, conductivity, it increased, resistance decreased from 2 into 10 raised to power 10 ohm to 5 into 10 raised to power 7 ohm. So now, it was possible to have colored antistatic or conductive compounds. Again, there was no significant trade-off which you had to do by adding single-walled carbon nanotube as comparison to the carbon. You add carbon, the compound becomes hard. You add carbon, the elongation at break decreases sometimes. But here you can see the effect was not that adverse. So the summary of all those tests were there was a major increase in tear and tensile strength without a trade-off on flexibility qualities like hardness, stiffness, and elongation. Then again, you get anti-static properties also with the possibility of adding in color, again without any trade-off on mechanical properties. Now some additional result in NR, SBR, particularly for automotive tires. This might come as a little exciting. These are the experimental results that we got in NR compound by using tube ball. In the middle radar you see, the middle point you see, that is the standard reference, and then there are two more triangles to it. One is with 0.2% and other one is with 0.5%. There was a significant improvement seen in abrasion resistance. Tensile strength also increased and compression strength also increased. So there was an unusual performance space expansion by using single wall carbon nanotube. Let me put a caveat here. Let me put a pause here that all the results I'm showing you, although as exciting they may seem, a lot of hard work and effort and failures have gone into producing them. Single wall carbon nanotube, like any new technology, are a subject of exploration and innovation. They are not a subject of adoption. The technology is not so common right now that you can just adopt it. It would require a certain urge of innovation, certain drive to fail and try and try and try again because of the sheer nature of technology and because of the sheer whole dimension of single wall carbon nanotube. So on slide, it may seem very easy and it may seem that, okay, in the first go you can get the results, but the result is not like that. You would have to put in effort to explore it, and at the end of this spectrum, the results would be much more fruitful if you can harness those potential. Let me carry on. Then NR and SBR tire compounds, these are some other results with 0.2%, 0.1%, and there is 3 recipes. We took 3 recipes, and you would see the results, the increase of results is all over the place. In some compounds, we saw very good abrasion resistance increase. In some compound, we saw energy efficiency increase, 10 delta at 60 degrees Celsius, 60 degrees was increased. In some compound, we saw a good increase in wet grip, in others we did not. There is a reason for that, and that reason is could be called as the variability of the test because of the orientation of single wall carbon nanotube, or simply to put it, how carbon nanotubes were compounded. This might come as a surprise to the conventional user of normal material in a sense that the results are pretty much regular or in a certain standard deviation range. Here you can see the results are very different. And we see it a lot when using single wall carbon nanotube. So you have to standardize your mixing procedure. You have to find that sweet point of carrier media and the blending procedure to get a certain results in consistency. This is for motorcycle tires, where wet grip is very, very important. We used it, we did 2 trials, one with only oil, we increased the oil in the compound, and then we added carbon nanotubes plus oil. Oil we used here as a carrier, and it will be worthwhile to mention here that this compound, this enhanced compound, is commercially being used by our own internal manufacturing of UJET vehicles, which is an electric scooter, which essentially is a spin-off of Oxial. So this is a commercial result in front of you. We are using this. Now the applications are endless, and I'm pretty sure if you let your imagination run wild, you'll find many, many more things which can be done, like latex foam compression set can be increased in soothers, in condoms, in balloons and toy, meteorological balloons, in gloves where you need conductivity, in catheters. Again, I have to urge all the gentlemen in this room for one thing. I have to say that this is an innovation subject. This is not an adoption subject. And innovation always starts with an I. So please, ladies and gentlemen, put your effort into it, do study it, give it a try. The results at the end of the spectrum would be good. It would not come immediately like that, but again, innovation, it starts with an I. Thank you so much. If you have any questions?
Hello.
Dispersion of nanotubes or nanofillers into the rubber matrix that you have already mentioned. And you have worked with EPDM and all that. But commercially, when you use a rubber compound or making a rubber compound in an internal mixture or in a two-roll mill, how this could be dispersed easily or dispersed in a good form so that we can get all the physical properties as you have mentioned, the increase of tear strength, increase of tensile strength, all that. Do you have studied it that it can be directly added to the rubber compound during the mixing operation of in a two-roll mixing mill or in an internal mixture so that it can be used widely commercially? That at the moment it is restricted because of the dispersion problem.
Absolutely right. I would 100% agree to you. Now, the technology development stage that Oxial Air is at right now could pinpoint the levers or the factors of success. That means now we know that the selection of carrier media and the blending technique, the compounding technique, both play a very, very important role in finding end results. How much, to what level, an exact mixing protocol has to be seen after trying out with the compound. I've shown you the results where whole recipe of the compound were exactly identical. What we changed was only the carrier media of single-wall carbon nanotube. There was DOA and there was DOS. Even when we changed these two factors and the addition ratio was very, very small, we used 0.1% of single-wall carbon nanotube, and that is 10% ratio. So we use only 1% of carrier media. By changing this 1% carrier media, the results changed. So right now our understanding is there are two levers. One is selection of carrier media, other is the blending technique. And these have to be carefully observed in each and every compound in itself to find out what would be the ideal and what would be the perfect condition for using single-wall carbon nanotube. So long answer short, it has to be tried and tested in that particular compound on those particular machines, blending machines, which we are open to do, by the way, and which I can proudly say a lot of our Indian partners are doing. They are present in this room, and they have got that confidence. They are using it right now. Sorry, I could not hear that.
Abrasion resistance properties, in abrasion resistance properties, how it can contribute to the abrasion resistance, say as a tire.
Okay, abrasion resistance. I can share the mechanism with you, how single-wall carbon nanotube add to abrasion resistance and tear resistance. By forming this percolating network of single-wall carbon nanotube, it is like a reinforcement of carbon nanotubes through the carrier matrix. What it does is, it takes the energy from one point and it spreads the energy out through the whole matrix. So the energy which was pinpointed at one point of abrasion is now spread out. Not only energy, the heat also, because carbon nanotubes are very good conductor of heat also. So the heat is also spread out more even. In fact, we have a commercial case where an OTR manufacturer is using this for better thermal conductivity, so that the tires are not heated a lot. So in that way, it contributes to abrasion resistance. Not only in elastomers, in fact, in almost all the polymers that we have observed, it increases abrasion resistance, it increases tear strength.
Okay, you covered most of my queries. I thank you for a wonderful presentation. It was really a very informative presentation. I have just a very small question right now. See, as you pointed out that this single carbon nanotubes are not new, But the problem was it was not available on a grand scale. That's what you were doing. Okay, so what would be a cost from the cost implication side? What would be the effect? Okay, you are showing a use of 1%, that's fine, but still, what would be a cost implication from a user end side?
That's a very interesting question, and the hardest question I've ever been asked, by the way. So, the cost implication would a lot depend upon how much we put in. That is a single factor of percentage, but how much can we use? In terms of tire, we are focusing and we are targeting not only premium application, but also commodity application, all the passenger cars. That means we are not targeting a price addition of several dollars. We are targeting a price addition of few cents maybe. So that is the window which we are looking at, a commodity application. So that would just give you an indication of what we plan to do. Our intention is to increase this whole consumption at a commodity size, and that is the reason we installed a 10-ton reactor when the global consumption of carbon nanotube was 450 kg. The global consumption was 450 kilogram, and we had a 10-ton reactor. The reason is we want to bring the cost down, and we can easily bring the cost down once the technology is there to consume it.
Can I just ask a quick question?
Please.
What kind of improvement in tan delta could you see? And theoretically, what kind of improvement in fuel use efficiency you would expect?
Fuel efficiency, you said, and what was the other one? Sorry, I could not hear that. Can you repeat the question, please?
Tan delta.
Okay. In terms of fuel efficiency, it was a trade-off that we felt. It was a bitter trade-off between wet grip and fuel efficiency. What we requested the manufacturer, the owner of the compound, was to adjust the whole formulation in a way that the formulation itself can compromise a little bit on wet grip, and by adding carbon nanotube, we can get that wet grip back.
Now, in one of the slides, you showed that your tan delta is improving. Can I know to what extent, what % improvement?
Till what percentage? I don't have the data, I'm sorry, offhand, but I can definitely mail it to you. But it's a very interesting question you have asked, and very right question, because it's always a trade-off between fuel efficiency and tan delta. And the beauty was the compounder or the owner of the tire, the manufacturer of the tire, had to adjust in that way so that he can live with that trade-off.
Hello. So what is the effect of the bony viscosity?
I have to check that. I'm sorry, I do not have answer on that. I'm not a rubber technologist as such.
And is it increases the cutting and chunking resistance?
Well, I would have to check that. I can't comment it off, and I don't have data on my hand for that right now.
Okay.
Yeah, I can tell you one thing. There is a significant thixotropy or pseudo-viscosity development with single-wall carbon nanotube. That much I can tell you, and we can hypothesize on that. But I don't have ready data on my hand right now. I can make it available. But thixotropy increases because you are adding something like here, something long and flexible to your compound, which would stop the shear, which would add to the thixotropy. It can become a challenge sometime in compounding.
I have a question. Do you need to partially oxidize to activate the surface for better dispersion? And my second question is that, have you done a study with multi-wall carbon nanotube also?
Oxidation or any kind of functionalization we do for some very specific projects. To be very honest and transparent, till now for any commodity application we have not seen oxidation or functionalization helping. You have those products in the market, but you would analyze and you would observe that those products which are functionalized or which are oxidized are used in very niche applications or for biopharma or just research purpose. Right now we are using raw carbon nanotubes which are about 80% pure. To come to your second question, but that saying that we do have the capability of functionalizing carbon nanotubes. And if we feel that at some point in time, we can give functionalized carbon nanotube which can bring about that effect, because it's not only about the property effect, it's also about the commercialization. It has to be in that domain. The price addition has to be in that domain which end customer can sustain. If we feel that, we can do that. We are developing some program for that already. Second question regarding multi-walled carbon nanotube. Oxyl doesn't produce multi-walled carbon nanotube. There is a lot of literature, but we don't do any work in multi-walled carbon nanotube, so I don't have much knowledge in that. Thumb rule is multi-walled carbon nanotube versus single-walled carbon nanotube. The usage is many times less, about 20 times to 50 times less, because multi-walled carbon nanotube is single-walled carbon nanotube one over other. It's like a spiral.
Good afternoon, Ravi. I have a question that I've been working with NR and 603, matrix 603. I have observed one typical problem that if I mix the compound and keep it for a longer period of time, say 15, 20 days, and thereafter I find that some phase separation is taking place.
Phase separation?
Yeah. Issue? So my question is that why it is happening and what is the root cause of it?
Okay. In NR and NBR, this is not a very commonly phased phenomena by us. If it is a low viscosity polymer, it is a commonly phased phenomena. The reason I think would be the same for NR or any other polymer. The surface energy of single-walled carbon nanotube is extremely high. So it would tend to get a phase separation. Until you mix it to that level, until you blend it to that level, that it kind of binds all the polymer, it kind of binds in the polymer chain. Then that phase separation doesn't happen. And the phase separation which we initially see after mixing is a very low energy phase separation. That means if you just put a little more energy into it, it would dissipate. But yeah, energy difference is the primary reason, and that is one challenge which has to be taken care of while blending. Thank you.
Thank you. Thank you.
Hello. Give some application in non-black compounds.
Application in non-black compounds. Yeah, this is the question I usually and my team usually ask to you, but through the learning I can share what are the end application. Solid tires, which have to be used in clean room, has to be colored, because they have to be used in clean room. You can't use black color because you won't be able to figure out how dirty is the tire. That is one huge application one. Second is in terms of sorting and branding. For example, if you have a particular hose of a particular make, if you would like to keep it separate by visual appearance from other, you would always like to have color in that. So in terms of sorting, as I would like to quote Henry Ford here, who said, I can give you a car in any color as long as it is black. So it is something like that. As long as you don't have that option with you, you would stick to black. But if you have the option of coloring, you would start wanting more colors. And key reason of that is it always helps to have colors in terms of sorting during production. It increases the efficiency. One more important point here is, since we are talking of all the elastomers, in pharma application, pharmaceutical application, you need colors. You need colors or pastel colors, light colors, where you can see the dirt, fungus, or any such kind of adulteration on top of it. So any application which has to be clean needs to be colored. Any application which has to be fancy needs to be colored. So these are two most common examples.
I have a question, sir. We have been working with this material for, I think most of the tire industry is quietly working on this material because of new innovations. I understand earlier this material is offered in a polymer based and maybe around 3 to 4 years before, but now you have changed to oil based. Is there any specific reason why you have changed for this?
I'm very glad you asked that question. Yeah, it was a result of about 3.5 years of our continuous research, not only our research, your feedback also, your eminent feedback. You have very good technologists on your board. So it was a result of, it is a technological upgrade that we could find out that by using low aromatic oil, which is easy to be used in existing formulations, we could get better dispersion. So it was a result of constant evolution, constant failures, I would say, that we could come to that level. So we have a better master batch which can disperse much easier now. If you would take an approach 4 years back, as you say, the paste form was very difficult to use. If you go back 10 years, raw carbon nanotube, extremely difficult. There was no commercial case. But now, since we are using these carriers which are already being used by industry, the commercial cases and the chances of success have increased a lot.
Any other questions? Please. We have sufficient time. If there's no other questions, we appreciate Mr. Ravi for his excellent presentation on this. You have covered on the usage of single wall tube in the
one question.
As well as on that.
Sir, one question to Mr. Ravi. Sir, in old raw nanotubes, is it able to recycle it, and how long it will sustain? And in rubber industry, the recycling process, how long it will sustain? That is the one question, sir.
Well, you cannot extract, with the present technological advances, you cannot extract single wall carbon nanotube once it goes inside any polymer. So you cannot take them out only. But if you recycle the compound whole, it would be with the compound. It stays with the compound forever. So if that answers your question, you cannot recycle as a single wall carbon compound, carbon nanotube once they go inside.